So one thing I forgot to add to the lesson on finding the inverse of a matrix is one of the uses of these concepts. Not it's used for more than one thing, but one use that is related to two homework problems actually on this section is solving certain linear systems using the inverse of a matrix. I'm going to make some comments in which situations are suitable for this, because you will quickly see that if you have actually only one system to solve, probably finding the inverse is not the shortest way to go about. And furthermore, not all systems can be solved using the inverse of a matrix. So right off the bat, let's actually mention clearly here as a remark that what I'm going to show you applies only to linear systems with the same number of equations and unknowns. For which the inverse exists. For which the inverse exists. Because remember, not all matrices have an inverse, and I'm talking about the inverse of the coefficient matrix. And another way of putting it, as you will see later, because that's equivalent to what I just wrote here, these are situations in which there is a unique solution. So systems, n by n systems that have a unique solution. So you should take your time, pause the video and write this down, because it's important to keep in mind this limitation. Only for n by n systems, same number of equations and unknowns, for which the inverse exists, and that it will lead immediately to realizing that this actually works only when you have a unique solution in the system. If you have the analogy with real numbers, you'll see why that's the case. Because let's take a break from matrices and look what happens to real numbers. So let's say you have this simple equation, a times x equals b, where a and b are given real numbers. Now, if you're not careful, you would say, okay, to find x, you just divide by a, right? So I mean x equals b over a, which is the same way as saying x is b times a inverse. But remember, not every real number has an inverse. For that to happen, you need a not equal to 0. Only in that case you have basically this solution. So only in that case you have a unique solution, which is given by multiplying the inverse to the right hand side. And I'm going to be even pickier, because in the case of matrices, multiplication is not commutative. The idea is that if you have basically a equation involving real numbers and the coefficient of the unknown, to look at this example, has an inverse, what you do, you multiply by its inverse on both sides, and that will make 1 on the left side, and then your solution is 5 inverse times 7, which is the same as 7 times 5 inverse. But again, for matrices, the order of multiplication matters, because remember, in general, a times b is not equal to b times a. So it will matter whether we multiply to the left or right. What we try to do with the inverse of a matrix is the equivalent for matrices of this type of process. So you have an equation, but this time you have a system which can be written in terms of a matrix times the column of the unknowns, basically. And then if we multiply by the inverse on the left side, this way you can, and if you have an inverse for that matrix, you can actually find the solution using the inverse. So let's actually start with an example. Let's say you have a 2 by 2 system, 3x plus 7y equals 12, 2x plus 5y equals minus 4. So why did I make this digression with real numbers? Well, if you use matrix multiplication, you notice you could write the whole system in terms of a matrix of the coefficients of the system times a column matrix which captures the unknowns of this system. And the right-hand side can be, again, comprised into a column of real numbers. So it's analogous to what you have for real numbers. A times x equals b, except now by x you mean a column of the unknowns. So sometimes in books this is given by big X. So big X will be a column matrix, which is again contains all the unknowns. A will be the coefficients matrix of the system, and the right hand side you can call it B. B is also a column matrix, which encapsulates the right hand side of the system. So it's analogous to real numbers, right? I mean, a system like this can be written in terms of matrices and matrix operations as A times X equals B. Now you should pause for a moment and convince yourself that this is indeed the matrix multiplication, right? So what do you get if you multiply a 2 by 2 matrix with a 2 by 1 matrix? Well, that gives you a 2 by 1 matrix, which is essentially the left side of the system, right? You will multiply row 1, right, times the column 1, which is 3 times x plus 7 times y. So that's the entry on the left. 2 times x plus 5 times y, that's the second entry on the left. So it's simply rewriting the system using matrix multiplication. So then the question is, okay, what if the matrix A, the left side, has an inverse? A inverse. Well, then I can take the system and I can multiply both sides on the left by A inverse. So then I'm going to have A inverse big X equals A inverse times B. And then A inverse, remember, is the identity matrix. In our case, it's, well, let's write AIN, right? Because in general, you have n rows and n columns. And remember, the identity matrix multiplied by any matrix leaves that matrix intact, just like the role of 1 for multiplication. So basically, A minus A inverse times B will be the unique solution of the system. Again, provided you have the same number of rows and columns so that the inverse has the potential to exist. It's not guaranteed to exist, even if it's a square matrix. But if it does exist, and if you multiply by the inverse on both sides, then you basically find the solution, which happens to be a unique solution. So if the system doesn't have a unique solution, you won't be able to find this inverse in the first place. If you study linear algebra, that won't be the case in this class, obviously, but you will see that these statements are equivalent. Having a unique solution, the existence of an inverse, there's something also called determinant, which also can characterize this situation. So these situations are equivalent. The fact that you have an inverse is the reason that you have a unique solution, that you can find it using that inverse. So let's actually illustrate how this works with this example. So I'm going to write on the second page again the system, and we're going to do the matrix the inverse matrix. All right, so we have the system written again the way it's given in the beginning, and then we have the system, the same system in the matrix form. And if we want to solve the system using the inverse, the first thing to do is to find the inverse of the matrix of the coefficients. So as you know already from the previous part of the lesson, let's augment the given matrix by the by the identity matrix. Don't rush to divide by 3 to produce a 1 because we have 2 underneath. The easiest way to make 1 on the first position is to subtract row 2 from row 1 and replace row 1. So we have 3 minus 2, 7 minus 5, which is 2, 1 minus 0, 0 minus 1. 2501. Then we need to produce 0 instead of 2 below the leading 1. So we do minus 2 row 1 plus row 2 and replace row 2. Remember to go slower, pause, and try to do the computation on your paper. I don't take too many breaks, remember, because I expect you to pause whenever you need more time to do the computation. So that makes the video not that long, and because again, you have the pause feature, so you should use it all the time. So minus 2 times 1 plus 2 is 0, minus 2 times 2 minus 4 plus 5 is 1, which is nice. Already I have the leading 1 there. Minus 2 times 1 plus 0. And then the last entry, minus 1 times minus 2 plus 1, makes it 3. The only thing left to do is, because now we are in the REF form, we need to produce the reduced row echelon form. So I need to produce 0 above the second leading 1. So to do that, at this stage, we're going to do minus 2 row 2 plus row 1 and replace row 1. Copy the bottom row. Minus 2 plus 2, 0. Now we do minus 2 times minus 2 plus 1. That makes it 5. And then minus 2 times 3 minus 1, minus 7. So because we ended up with the identity matrix on the left, it means that A has an inverse. And it is what we got on the right hand side. Or, I mean, on the right of the vertical bar. 5 minus 7 minus 2 and 3. So, now to solve the system, we multiply by the matrix, the inverse matrix on both sides. So we start with the system in the matrix form, and by multiplying to the inverse, remember that on the left you're going to end up with the identity. You don't actually need to do the actual computation unless you want to check to see if you're right. But if you're correct, when you multiply on the left by the inverse, you should end up with 1001 on the left side. And on the right hand side, you're going to have to come up with what you get with the matrix multiplication. So you multiply by the inverse on both sides. And then on the right hand side, you will have essentially the solution of the system. The identity times xy is just xy. You don't even have to write the identity anymore, because you know that if you multiply by the inverse on the left, the effect of it is essentially canceling that matrix. So on the left side, you end up with xy. And on the right hand side, let's do the multiplication carefully. Row 1 times the only column that you have in the column matrix, plus minus 7 minus 4. And then row 2, and then the same column, minus 2, 12, plus 3 minus 4. So that's 60 plus 28 minus 24 minus 12. That gives me 88 and then minus 36. So x will be 88, y will be minus 36. So plug them in into the system to convince yourself that these are the solutions indeed. And then I'll have a little extra remark before we call it a day. So in a nutshell, this is how you solve a system using inverses. Here's the remark. In general, unless you are required to do that by the problem, in general, the Gaussian elimination is faster to begin with. So you just basically start with the augmented matrix, and then you proceed to produce the REF or RREF depending on your preference. Not to mention that the Gaussian elimination works for all systems. Remember that. For all systems, not just the ones that have the same number of unknowns and equations, not just for those who have a unique solution, not just for those who don't have any solutions. So if you have a system to solve and nothing else, and you have a choice of which method to use, then Gaussian elimination is probably the way to go. The inverse of a matrix really makes sense, especially if you use computer algebra systems, and especially if you use multiple right-hand sides of the same left-hand side of the system. So for example, imagine that the left side of the equation are some constraints in some business planning. So for example, maybe, you multiply a different number of units of several products by cost or price per unit, and you want to run some scenarios in which these constraints are set equal to various numbers. Maybe 12 minus 4, like it was in this case, maybe some other values, 1, 2, maybe 3, 6, maybe 5, 7, and so on. So it's like solving multiple systems, but with the same right-hand side, with the same left-hand side. Especially if you implement the algorithm in a computer algebra system, or maybe even on something more basic like Excel, then you could find the inverse once and for all, and then the solution is simply multiplying that inverse by various inputs on the right-hand side. So once you compute the inverse, in this case, the inverse was, like I said before, 3, 7, 3, and 5. Then you can solve multiple systems like that by simply multiplying that inverse to the right-hand side of what you have. So 12 minus 4, it's what we did. Then you can multiply by the next input, 1, 2, and so on and so forth. So in that sense, this method is useful, because otherwise, if you have a single system, it's probably easier and more comprehensive actually to go by Gaussian elimination. But if you know that the system has a unique solution, and if you have multiple right-hand sides, then you could find the inverse. For our class, the problem will mention clearly, if I give such a problem in the exam, use the inverse to solve a system. Otherwise, just use the Gaussian elimination like we did before. There will be other uses of inverses for various algorithms later, and we'll talk about that when the time comes. Okay, so for now, that completes lesson 3.3.